I'm very sorry for my missing the last class. So I got flu. So fortunately, my test result is not negative, not positive for the H1N1. So it's just a seasonal flu. Are you sure? So if we are not sure, so you can leave. So it is my first time even to see Tamiflu. So I took, just in case I took the Tamiflu for 5 days. So, but this year I heard from my doctor, there is a lot of people who already got the flu shot, also got the flu because it's kind of the mismatch in year. So CDC designed the flu vaccine based on the 3 years ago. So it's every the 3 years, so it will be the outbreak. It's not outbreak based on the, so if you remember the 3 years ago, there was the H1N1 swine flu, so it was the outbreak. So it is based on that, but this time even seasonal flu, many flu are not actually based on that H1N1 is another type of the flu. So if you have a child or children, so I strongly suggest to check your flu vaccine or whatever, and also even yourself. So even though this is the second time to miss my class because of my illness. The first one, last one, I cannot remember, but several years ago I missed it because of my illness. But because of flu, it's my first time. So do not believe the 100% for your flu shot, but definitely something is better than nothing. You should take your flu shot if you are not. Okay, but I don't think I'm fully recovered. So, but I'm going to try, which means do I have the flu virus? I'm not sure, but probably it is recovered. I took the Tamiflu and some antibiotic, so and some others. So, but still a little bit. Sometimes tired. I can feel such a tiredness, but I will try my best to do the lecture. I think the GA, the D covered the thread. Fortunately, the lesser part of the chapter 4 are not very difficult to understand. So we already covered some part of the chapter 4. So I believe that my student can cover the chapter 4. With the help of the GA. So today we are going to go ahead the next topic, which is the synchronization. As we have discussed a lot, even that is not possible, it's impossible to have the unlimited resource of the computer. But think about if we have the unlimited resource of the computer, then many of the algorithms, many part of our textbook will be eliminated. However, unfortunately, it's not possible. So most of the time, the algorithm in operating system are struggling from how to share the data. Okay, that is a big problem. No matter what types of the CPU or how big your memory size is. So anyway, we are struggling. We are fighting with how to share the data. So this is the same problem, process synchronization. So somebody said the 90% of the code in operating system, as you know, the operating system is also the software. It's a group of the software to coordinate and control the resource of the computer between the computer and what? The user. So it's kind of the interface. But the 90% of them are actually related to the synchronization. Of course, the operating system consists of the many processors. There is not any some of the embedded operating system use a single process, the operating system, but most of them are the concurrent. The processes, the many processes are working together for the limited resource. So many of the code itself include how to synchronize. So we need to understand what is a synchronization problem and how to address such a problem. So we will see first the the race condition first. Okay, so how many processes we have? We have the multiple processes. They are accessing sometimes their own data in the memory segment, but mostly they are accessing, they are shared, they are work together concurrently with the other processor, which means you need to, for example, if we are using the IPC for the communication based on the shared memory, you need to allocate the specific area on the memory. Usually it's in the processor segment, but you can give the permission to other process, then you can share such a memory area for the communication. At that time, so if the several processes involved for that the activity for the shared data at the same time, okay? So they are fighting. Sometimes this is my area, so I try to update the data. At the same time, can the other process update the data or access the data? At the time, this kind of the condition is called the race condition. So race condition involves first several processes, not just one process, but many processes. At least the two processes are involved. For what? The shared data. If each process, even though we have the many processes, but each process deals with their own data, there might be no problem. They can use, each process can use their own data, but in case the many processes are accessing the same data, shared data concurrently, so that is called the race condition 1, because they are racing to get the ownership of such a data. So we need to coordinate. So we need to do something to arrange such a race condition that is called synchronization problem. In other words, in terms of operating system, I'd like to synchronize the data status for the shared data status along the multiple processes. So that is the race condition. So we need to do the synchronization to address the problem of the race condition. So at that time, we can understand the race condition synchronization problem in terms of a producer and consumer problem, as we have used in the before. So producer, it can generate, it can provide the data, and consumer can consume use such a data. Okay, so let me simplify such a race condition. So let's say we have the two processes. One is the increase the value, like a counter. Okay, one is the increase the value like this one, so plus 1, and another process is the minus, so decrement. So we can actually implement this code as the instruction. So we the data from the register from the shared memory, the counter to the register 1, and we can use the plus 1. What is the instruction that can increase by 1? Increment. Okay, in terms of the assembly language, increment. So then we can save such a register data, incremented data into the shared memory. This is one operation by the processor A. Another one is the same thing. It uses the shared memory from the counter, read the data to the register 2 or their own register. So if we are using the two processor, multiple processor, each processor can have their own register. Even single processor can share the CPU time sharing. So you can use another register and decrement the subtract by 1. Okay? Then save such a decrement data into the counter. Then at that time, so let's say the counter, the shared data value is a 5 initially. What will be the output when you learn the same time? This one and this one, two processes. As we had discussed before the last week, it can be 5, right? It can be 4, can be also 6. So we cannot guarantee. This situation is called race condition. If we cannot guarantee the output, that means it's not synchronized. So we need to address that problem. We need to synchronize that problem. This is just one example in operating system. It's many happen. So we need to, in your operating system, we need to address that. Okay. So this is one of the example of the sequence of the execution. Okay. So for example, let's see the other. So we have the two. This is a case in case of the multiple processor, but it's the same problem even though we have the single processor. Doesn't matter. So if we have the single processor, we can share the CPU time. So then the CPU scheduler will work to select them. Okay, so we have the shared memory data. Then the process producer, the process 1, will access the data and increase, then write the data. In terms of the producer, it's supposed to be 6. And similarly, in terms of the consumer, another process is supposed to be 4. Okay, but output can be various. That is the race condition. So one of the examples is first, there are different possibilities. There are different ways to execute this one. First one is we can execute the producer first, like this, read the data and increment and store the data, read the data into the memory, like this one. Okay. Then the next one is the read the data again and decrement and write back the register data into the shared counter. Okay. So this is a race condition in terms of the assembly language. Then this is a first case. First case is interleaved one, which means we are going to execute the instruction first, then this instruction, this one, this one, this one, and this one. Okay. So for example, so producer read the data, then the consumer read the data. So both of them are 5 in their own register. Then increment in the producer and the decrement in the consumer. Okay. Then write back to the memory is a 6, and write back to the memory is a 4. So finally, it's going to be 4 in this case. Okay. The next case is we are going to start from the consumer, another process first, then interleave. So similarly, it will be the 5 and the 6 because this is the last instruction. To store the data of the register 1 to the shared memory. So it will be 6. Okay. And the last case is we can execute the the producer first, then the consumer last, and the vice versa. So we can run the consumer first, then the producer next. The output, as you can imagine, it will be the 5. So there are 3 different cases. So even though we are executing the same code, but depending on how to execute, so it can be 4, it can be 5, it can be 6. So we need to address such a problem that is the synchronization problem. So most of the operating system, how can handle that? But in very, very high level, how can you address such a problem? In case of the race condition, very, very high level. You can use log. Okay. So what if the one process access the data, you can log such a shared data. Then you can do whatever you want until end of the operation. And if you are done, you can release the log. So that is the simplest way, but the main problem is deficiency.
No. Performances.
Performance. Why? While one process is holding the log for the shared data, all the other process should wait. Who want to access the shared data? that is fine if your operating system is very simple, like just accessing the one data. But in general, so if as you can imagine, there are a lot of such a synchronization problem. So it's not okay in terms of the performance because the entire system maybe the hang, the stop because of the locking. So locking however, it is true. Many of the, almost all the such a synchronization problem can be solved by kind of a locking mechanism. We are going to define different lock, shared lock, explosive lock, and different types of lock. So we will use something, the instruction level lock, or the mutex lock. So to address such a problem, so we are going to define critical section problem, which means, so we are going to very high level design the process structure with critical section. What is the critical section? Here, critical section is a part of the code in a process where the operation access shared data. Because if we use just a simple locking mechanism, because of such a lock, all the other process who want to access the code should wait until entire process is end. Okay? So why don't we define the part of the process code as the critical section where the operation need to access shared data? That is the critical section. So that is a critical section. And in addition to the critical section, the process has entry section before critical section. And after critical section, it has the exit section, then remainder section. That means, so we can view the process as the full part. Okay? It's kind of the repeating the operation. Okay? Whenever we access the shared data, it should enter the critical section and exit the critical section. So this part, critical section, we can access the shared data. So this part is before you enter the critical section, entry section. And when you leave the critical section, it's the exit section. Then the other part is the remainder section. If we do not consider the critical section problem, this entry section and exit section, we don't have such a two part, just the critical section and remainder part. Okay, so can you guess what is the main purpose of the entry section and exit section? If we consider just a simple locking mechanism, this is kind of acquire the lock and release the lock. Okay, but still that is not enough. During that time, the other process are waiting. And also, one of the main problem of the locking mechanism will be starvation. What is a starvation? Hungry. Right? For example, I got the lock to access this file. Then next, all the other students are waiting to mark the attendance to attend the coming because you coming the late. But next, the GA take the disk file, and next me and him. And if we toss each other, the other student cannot get the lock for this. That may happen. That is called starvation. Okay, some process may not get the permission to access this one. So during the entry section, we need to do something to not only just getting the lock, we need to do something to be fair. Fairness, I'm not sure whether that's correct, but anyway, to do something to solve the problem of the race condition for all the process. So that is entry section. Then, when you leave such a critical section, which means when you finish to access the shared data, you need to do something like the release the lock or give the information to others. So I'm done. So if someone else other process need to access the critical section, you can do that, something like that. That is the exit section. So depending also throughout the chapter 5, we will discuss about the mainly how to implement entry section and exit section. For what? To solve the problem of synchronization. To address the race condition. Okay, so this is the structure, process structure. Okay, so this is the kind of the code to implement in terms of the critical section problem for the process gate, which means so we has a without critical section problem, the rectangular part, the box is not considered. But if we consider the critical section problem for the process, we have the this and we have the this. This is the entry section of the critical section. When you leave, when you finish to access the shared the information, we can leave and do something exit section. So can you understand what that means? Y turn is equal to J. Turn means it's the variable. Okay, so global variable for all processes. Then this one is kind of a lock. Okay, decide who will access the data. So for example, if turn is J, that is true. What that mean? So it's can enter the critical section or not? Can, because it's a turn if so for example 0. Okay? So turn is 0, then this is not, turn is not if J is 1. This is a process I. I think that, why don't we use a C? Instead of I and J, why don't you use process 0? This is a process 0. So this is the first turn is equal to 0. Okay? Then, you see, the J is equal to 1. J equal to 1. So, whether this turn is other or not. Okay? Right now, it's a 0 turn. So, process is 0 turn, which means it's a false. So, you can leave while loop. Then you can enter the critical section. Then you can access the data. What about if this one is turn is equal to 1? So turn is equal to 1. So 1 is equal to is true, which means another process, process 1. Process 1 is accessing the data, critical section data. So this entry section determine whose turn is there. Okay? So one process can enter the critical section. During the critical section, right now, turn is still the 1. So turn is, this is a 0. Okay? So this is a 0. Still, this process 0 is accessing the critical section. When this process 0 is done to access the shared data, then changing during the exit, change turn is equal to 1. Another process. Then process 1 has the same data structure, process data structure, and critical section, and exit section, and remainder section. It's the same thing. And Y turn is equal to 0. So if this one is changing to 1, so turn is 1, so it's not, so can enter critical section. However, during the critical section, is a turn is a 0, turn is a 0, still 0, other, so cannot enter critical section. Okay, this is based on the very basic the locking mechanism to solve the problem of the critical section. synchronization problem. So we will use such a process structure, the critical section process structure, to discuss about how to address the race condition, how to implement the critical the synchronization problem. Yes.
This code is again setting the turn to J.
Mm-hmm.
So isn't it just repeating this?
This is not the complete code of the synchronization. You don't have to worry with it. Just to show how each process is organized. Okay? So we will see details. Okay? But simply, this one is the simplest way. It's one of the way, but not perfect. So, for example, there might be a lot of problems. In this case, the axis section can actually decide who is the next term. Okay? In this case, the axis section decide. In this case, the J. Process I, process 0 determine the next one. Okay? So that is the one of the way, simplest way. But it has a lot of problems. What kind of problem? First, we need to discuss about the requirement of the critical section problem. There are 3 requirements to solve the synchronization problem in terms of critical section problem. So if we determine the process structure consists of the entry section and critical section, exit section, actually basically the in between the critical section, we put the entry and exit. So that is the algorithm that we are going to focus on. So how can we implement when we implement such an algorithm, that algorithm should satisfy with the 3 requirements. The first one is a mutual exclusion. What does that mean, mutual exclusion? Share the data. How many processes anyway can access the data at the same time? Only one. Okay, that is true. So even though it's a shared data, only one process should be able to access the data. Okay, otherwise it will cause the race condition, right? It will cause the synchronization problem. So first one is it's obvious. Only one process can enter critical section, share the data. That is the mutual exclusion. So when you develop, so as I said, operating system actually consists of a bunch of the critical section problem. So is there any general solution? No. Sometimes depending on the situation and algorithm, you use different one. But when you implement such the synchronization problem, which is based on the critical section, first you need to consider whether this one is the mutual exclusion or not. How many processes can access the shared data, which means critical section at the same time. Only one process. Progress. I think the bounded weighting may be easier to understand. Bounded weighting means, so in how many processes in critical section? Only one, right? What if there are more processes, like process, in case of process 0 and 1, so this is a process 0. Process 0 is accessing. The other process 1 is waiting, right, to access the data. And what if there are 5 other processes? So there it is possible. We have the shared data. There are 5 other students. So right now I'm using this 5, but the other 5 students are waiting to mark their attendance. So at that time, that waiting time should be bounded. Is the bounded waiting means it's a short time, long time, we don't know. But it has the upper bound. It's not forever. Okay? At certain time, it can be millions of years later. It can be 10 millions of the later, but it should be bounded, guaranteed. Okay? Don't be confused with the bounded waiting is a short time. Okay? It's not short time. We don't know how long it takes, but guaranteed. That is the bounded waiting. Another, the concept of the operating system which is easily confused is real-time processing. What is a real-time processing? Real-time operating system. I think have you ever heard about the real-time system? Real-time operating system? real time. Real time operating system or real time processing. What does that mean, real time?
Once.
It's a very fast.
When actually, I guess when actually it is working not as an idle state or nothing. That time.
I think that she is correct. Can you understand? Real time operating system. Real time means it's not fast. Okay? We don't know what is a fast. Right? What is a fast? So 100 miles per second is a fast. For the 10 meters per second is fast. It's a very relative. We cannot, it's a very subjective. We cannot say the 1 millisecond is a faster than what? So we cannot say whether this is a fast operating system, faster system. Instead, real-time operating system means guaranteed. Okay? Guaranteed means, so for example, think about I have the new device to identify the smoke, okay, chemical in the room. So this operating system should work, should detect the smoke, okay, within 1 second. Okay, should be guaranteed. No matter what situation, it should be working alarm within 1 second. Okay. For example, even though there are 10 or 1,000 of the smoke in this room, this device should alarm, okay, within 1 second, guaranteed. Okay. Even though this is a very busy, this device is very busy to display the something, the interface and play the music and video, but the main thing is it should return the alarm within 1 second. Okay? Your algorithm should consider something priority, whatever, to guarantee the given time to act something. That is a real-time operating system, real-time processing. Very, very mission-critical system. It should be real-time, but mostly such a real-time operating system can be considered in general very fast system. So similarly, so when we consider such a critical section problem, bounded waiting means at certain time, anyway, waiting time will not be infinite. Okay? It's a finite, it's a bounded. At certain time, it will get the time, chance to access what? The critical section, to enter the critical section. That is the bounded way. Okay? The second thing is the progress. It shows if no process is executing in its critical section and some process wish to enter the critical section, and you, anyone who can understand and explain? The progress means you can actually understand from the title, progress. If somebody wants, if there exists a process that wants to access the shared data, will get the access the critical section. Progress. From the, you can understand progress as the, from the entry section means you show your intention. I'd like to access the critical section, share the data. Once you express your intention to access the data, eventually your intention will be progress. You will access the critical section, to share the data. That is the progress, which means no process is executed in critical section, which means that sometimes one process use the critical section forever, right? If we consider extreme case. In that case, no other process can access the critical section. That is true. So to limit such a case, so if no process is executed, no process in the critical section, And there exists the process who wanna access the critical section. There are processes who are waiting to access the critical section. Then this process should not be in the remainder, which means where's the remainder? Which means here, which means already use the critical section. Do not express to enter entry section. So only process who really want to access the critical section. Among them, that is called the candidate, the process. Such a among candidate process, the one of the candidate process will be selected as the process to access the critical section. And such a waiting time should not be postponed forever. That is quite similar as the bounded waiting, but bounded waiting is in terms of for each process. But this one, progress means for all the process in the kind of pool of the process that want to access the critical section. So there are three requirements when we solve the problem of the critical section. First one is obviously it's a mutually only one process can access the critical section. Second is the process who want to access the critical section, then their waiting should not be postponed forever. In other words, eventually will access the critical section among that process. Yes.
So it's then only those processes that are not in RC. RC stands for?
The remainder. Okay. If they are in the remainder, they already use the critical section. Okay. So this, but if the process want to access again this one, then that process is not the remainder section. I see. Okay. That process is considered as the process who want to access the data. Okay? But if the process is just after access section, we do not consider such a process. Okay? The reason why we consider such a the condition is if we consider again this one can be forever. Only one process may take the critical section. The other process will be waiting forever.
But I'm holding my remainder section because two processes are different, right? And they want to access this critical section, which is a shared memory.
Yes.
So what is supposed to be in the remainder section?
Remainder section their own code. So their own code.
Their own code.
Yes. It's their own code. So remainder section you don't have to worry about too much remainder section, only critical section where it's an operation, it's an instruction code and or part of the code that would like to access the shared data. And in between you need to consider something option. So that's the reason I gave sometimes it's hard to imagine, sometimes very high level and also sometimes very low level implementation. Why don't you think about the locking? Okay? To access the room, you need to get the lock. Okay? And you need to return the lock, the key. So that's the entry and exit section. Okay. However, if there exists more students who wanna access the room with the key, okay? So if you definitely it's not possible for two students share the key, right? Only one student can get the lock. That's the mutual exclusion. And also the next one, the progress. If you express, I wanna get the key, he wanna get the key, he wanna get the key, then eventually we'll decide among these people who is the next one to get the key, then to enter the room. Okay, that is the progress. And at the time, the reason why we consider the processor IC remainder section. So if I do not return, okay, then use it again. So it's forever. So the other processor, the other student cannot get the key to access the room. So that is the progress. And the last one is such a waiting time should be bounded. Okay, it's not short time, it's not long time. It should be bounded, not forever. That is the bounded waiting. Okay, so in terms of implementation, there are three types of the implementation. So if you do not understand the right of way, what is the critical section problem, just imagine the kind of the lock. Okay, getting the lock and release the lock. That is the simplest way. It's not perfect, but it's the simplest way. So, how can we implement such a lock, such a critical section software solution? We can use the code, programming code, to get the lock and release the lock to implement the critical section. So when the most of the software-based problem is the busy waiting. What is the busy waiting? You are waiting, but very busy. In other words, so I'd like to check whether key is available. Forever check. You ask the department, is there any available key? No, the next available key? Probably the department secretary will be crazy if you ask it every time, every second, right? That is a busy waiting. That's terrible for the system performance. That's kind of 100% CPU utilization. Okay? So that is a busy waiting. Hardware solution is like the real lock. Okay? Hardware instruction. Okay? Sometimes the US processor provide something instruction code. That is the hardware solution. Okay? And operating system solution is kind of software. Because operating system is like the software, but operating system is the system structure, data structure. We receive the mutex, okay, and semaphore, such as the operating system solution. Okay. First, algorithm. We will consider two process case, process 0, okay, and process 0 and process 1. Two process cases. So too simple, but it can be easily generalized to the n number of processes. So this one we already have seen before, simplest one. So we have the critical section where the processor would like to access the shared data, and remainder section, the other code that doesn't need any the shared information. So for the entry section, we need to check the ton. So what is a ton? Ton is the global variable that can be accessed by any process. Okay? So it determines the whose ton is that. 0 means process 0. 1 means process 1. I means process I. Okay? Then exit section is when this current process exit. Okay? Then so this is a process 0 case. Process 0 case. Then when this process 0 leave the critical section, give the permission to other. For example, process 1. Or sometimes it can be if that is n plus 1, something like the next one. So process it. This you can we can simplify the problem to process case, process 0 and process 1. So process this is a process 0, so next turn is a process 1. Okay?
But how does it access the while loop? Because turn we are initializing it as 0.
So that is the initial case. The first case is a 0. Okay? So process 0 can enter because it's not 0. Okay? So it can enter. So still it's a process 0. Turn is a process 0. At the same time, if process 1 would like to access the critical section, okay, and check the y turn is not 1 in the process 1 case. Check whether turn is not, which means it's a true while loop. So process 1 cannot enter the critical section. Once it's done, this process changes the global variable to 1. Turn is 1. This process turn is 1. This is 1. So this is a false. Then can enter critical section. Okay? This is the simplest case, like the locking, basic lock mechanism. So this is one of the solution, basic solution of the critical section problem. So we will check whether this satisfies with the condition. What about the mutual exclusion? How many processes can enter critical section? Only one. Who has the turn, right? Only one process can enter the critical section. It's not possible for two processes to access the critical section at the same time. So this is good. What about the bounded weighting? Bounded weighting, unless this is infinite, we do not assume that this is the forever. We cannot handle such a case. It's not critical section problem. As long as this is the finite, the code, it can be the next one can get the ton, right? So bounded time, bounded weighting is okay. What about the progress? What does that mean, progress? Progress means we can select the next process among the entry section who wanna access the data. Okay, critical section. Then, however, who determine the next one? Current process determine the next one. So if this one is set always 1, in case we have the 3 processes, 0, 1, 2, process 0, process 1, process 2. What about the process 2? It may not get, right? So it depends on the exit algorithm. Okay? Because of this one, sometimes it can set as the always 0 itself, right? Then the other process cannot get forever. Actually, this is not possible in terms of the progress because the remainder section cannot get. So it's not the terrible. It depends on the exit code, exit section. So it's math. So that is one of the problem. So the simplest way to access that. And next, it's a little bit change it. So we have 2 variables. One is the Boolean, the flag, okay, and we are using the flag information. So flag means so this flag is a number of process. The array is the number of flag, the processes. So if in case the 2 process cases, we have the flag 2, which means flag 0 is a process 0, and flag 1 is a process the 1. Okay. So initially we set the false. So false means in the flag, I'm not in critical section. Okay. I'm not using the shared data. Okay, so which means, so this is a process I. If you are confusing, it can be set as a 0, 0. This is a 1, and this is a 0. Okay. Then we have another process. The process, the 1. Process 1 is the same structure, flag. And has the same entry section, flag, critical section, and exit section is a flag. And remainder section. This is a Y. So let's see. So when process 0 enter the critical section, so then change it, flag 0, which means I'd like to access this flag indicate I'd like to access. I'd like to access the critical section. It's kind of intention. If this one is a false, false means not interested, not in critical section. Okay, so at that time. This is the entry section, so entering the entry section. So check whether flag 1 is in critical section or not. So currently no process in the critical section, which means flag 1 is a false. False means you can leave the while loop, then enter the critical section. But suppose that the process 1 is in the critical section, which means flag 1 is true. True means it's true for while loop, so forever. So while loop, you need to wait until what? When? Process 1 leave the critical section. When process 1 leave the critical section, it changes. I'm not in the critical section. So flag 1 is false. So flag 0, this case, so when in this case I enter the critical section because it's a false first time as a default. So enter the critical section. So then when this process is in, I'm not in. What is the main difference? Algorithm 2 and 1. Algorithm 1, when process exit the critical section, specify the next one. But this one, this process